You ever wonder how your phone can just, map your face in 3D? Or how a self-driving car sees the world around it? It really all boils down to one big question. How does a computer take a bunch of flat 2D pictures and build a three-dimensional world from them? Okay, let's just dive right in and pull back the curtain on the magic of computer vision. So here's our game plan. We're going to take a 5-step journey. We'll start with something super simple, just matching a tiny little group of pixels. But by the end, you'll see how that one little idea can scale up to create an entire 3D world. It's going to be a pretty cool ride. All right, first up, the pixel matching game. At its heart, the biggest problem for a computer is to look at two different photos of the same thing and find the exact same spot in both of them. It's basically just a super high-tech game of spot the difference. So how do they do it? Well, computers use this really slick method called block matching. The idea is so simple. You take a small square of pixels from one picture, and you just slide it all around the other picture looking for the place it fits the best. And to figure out the best fit, it uses a bit of math called the sum of squared differences, or just SSD. Let's see how that actually works. Okay, let's make this real. On the left, we've got this tiny 2x2 block of pixels. See the numbers? That's just their brightness. And on the right, that's the bigger area from the second photo where we're going to hunt for our little block. The goal is simple. Find where that little guy fits perfectly. Now, what's really cool here is just how simple the math is. I mean, look, for any spot, the computer just subtracts the pixel values, squares the difference, that's to get rid of any negative numbers, and then adds them all up. So on this first try, in the top left corner, we get a difference score of 652. Just remember, a higher score means it's a worse match. So the computer just chugs along, repeating that little calculation for every single possible position. And this table, well, it shows us the results. After checking all 4 spots, one of these things is not like the others. Would you look at that? At position 0, 1, the score is a tiny little 4. I think we have a winner. And that's really the whole trick. The lowest score wins, period. The computer now knows, with pretty high confidence, that it's found the matching patch of pixels in the other image. It's simple, it's elegant, and it's seriously powerful. Okay, so we've matched one tiny block. Big deal, right? Well, this is where the magic really starts. What happens when you do this for every single pixel in the whole picture? You get something amazing, something we can actually see and use. A depth map. We're going from pure math to an actual map. So the key idea here is something called disparity. It's just a fancy word for how much an object seems to shift between the left and right pictures. You can actually see this for yourself. Go on, try it. Hold your thumb out in front of you. Close your left eye, then open it and close your right. See how your thumb jumps back and forth? That jump is disparity. And notice, the closer your thumb is to your face, the bigger that jump is. It's the exact same thing for the computer. And this is what you get when you do all those calculations. This is a disparity map. The rule is super easy. The brighter the pixel, the bigger the disparity, which means the closer it is to the camera. You can totally see how the objects in the front are popping out in bright white while the stuff way in the back just fades to black. But wait, how do we get from a pixel shift to an actual distance, like in meters? Well, we use this little formula. As long as we know the distance between our two cameras, that's the baseline, and some details about the camera lens, that's the focal length, we can convert that disparity value we measured into a real-world depth measurement. And here is where it all clicks into place. By measuring the disparity for a pixel on that yellow building you see, and just plugging all the numbers into our formula, the computer calculates that the building is almost 27 meters away. We just measured the real world from 2 flat pictures. How cool is that? Now, in a perfect world, that would be the end of it. But the first result isn't always, perfect. You can get noise, you can get missing bits. But the great part is, we can actually go in and tune the algorithm to sharpen the computer's vision. I mean, just look at this. On the left, that's our first attempt at a disparity map. It's a little splotchy, right? But on the right, after a developer just tweaked a single number called blockSize, that's the size of that little search window we talked about, look what happens. Suddenly, pop, the back of the chair in the foreground is crystal clear. So the big takeaway here is that these algorithms aren't just set in stone. Developers have all these little knobs they can turn, these powerful levers they can pull. And tiny little tweaks in the code can lead to huge improvements in how well the computer actually sees and understands what's going on. Okay, up to now, we've been working with a pretty big assumption that our two cameras are perfectly parallel, looking straight ahead. But what happens in the real world? What if one is tilted just a little bit? Well, that throws a whole new wrench in the works. This is where a truly brilliant piece of math called the fundamental matrix comes into play. Just think of it like a cheat sheet for the computer. It's this small 3x3 grid of numbers that perfectly spells out the entire geometric relationship between the two cameras, no matter how they're angled. And this is what that cheat sheet actually does. It draws these things called epipolar lines. So instead of having to search the entire second image for a matching pixel, the fundamental matrix tells the computer, hey, don't waste your time. The point you're looking for is somewhere on this exact line. It makes the whole search process insanely faster and more accurate. All right, we've come a long way. We've gone from matching pixels to building depth maps to aligning our cameras. Now it's time for the grand finale. Let's scale this whole thing up and build an entire 3D world. So far, everything we've talked about uses just two pictures, a left and a right. But what if you have more than two? What if you have, say, dozens or even hundreds of photos from a video you shot just walking down the street?
That's when you bring out the big guns, a technique called structure from motion, or SFM. This is really the master algorithm. It looks at all the images at once, finds matching points across them, and it solves for two things at the same time: the 3D structure of the scene and where the camera was for every single photo. It's like solving a giant 3D jigsaw puzzle, but you don't have the picture on the box to help you.
And this is a peek under the hood at the computer's brain while it works. This log file is showing us all the intense number crunching happening in the background. It's matching thousands of features, running calculation after calculation, and slowly, piece by piece, building the geometry of the world from nothing but those flat images. And after all that thinking, this is it. This is what we get. We've gone from a collection of flat 2D photos to a complete 3D digital world. This point cloud is a digital twin of the real scene, built from nothing more than a handful of simple pictures. It's just incredible.
Which really leaves us with one last mind-bending thought. If computers can already do this, if they can rebuild our reality in 3 dimensions from simple photos, what new patterns, what new details, what new things are they going to start to see in our world that have always been completely invisible to our own eyes?